Hello and welcome back to Multidimensional Integration, the video series where we talk about the different kinds of integration we have in the space Rn. And indeed, in today's part 9, we will talk about the general integration we can do with polar coordinates in n dimensions. And to do that, we will combine the famous change of variables formula with the definition of a surface integral on a surface in Rn. However, as always, before we go into the details, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, as a Steady supporter or a Patreon member, you can easily download all the additional material with the link in the description. For example, there you find books, quizzes and PDF versions. And then without further ado, let's immediately start discussing the polar coordinates in Rn. In fact, it's just a straightforward generalization of the spherical coordinates that we have in our three-dimensional space. And there you might already know that such an integration formula might be especially helpful in problems where we have some particular symmetries given. And moreover, you should also already know that such polar coordinates can be described by the distance from the origin to the point and by some angles. And with this information, we can describe almost all points in the space uniquely. And I say almost because we don't need to describe all the points in Rn because we do an integration anyway. Which means we can totally ignore a set of Lebesgue measure 0 here on the right hand side. And we do that because then it's quite easy to write down a diffeomorphism phi. So you see, what we actually do here is just the change of variables formula. This means here on the left, we also have a subset of Rn. More precisely, it's an open subset and we can write it as a Cartesian product. And there the first coordinate should be the radius, so it goes from 0 to infinity. And the other ones are the angles, where only the first one has to go from 0 to 2 pi, where the other ones go from 0 to pi. So in that sense, it works exactly the same as in R3, we just need some more angles in addition. And now in order to keep it tidy, let's put all these intervals for the angles into an n-1 dimensional subset U. This means if we call an element from U theta, then this one has n-1 coordinates. And in order to keep it simple, let's call them theta 1, theta 2 and so on. Okay, and now most importantly, we have to write down the definition of our diffeomorphism phi. So the input is given by our n parameters and the first one we call r. This makes sense because it should be the radius and the other ones are our theta angles. And now you know the output of phi should be a vector in Rn as well. And there we just have to describe how we build the whole vector. And this is not so complicated because we always have the radius r in front and then we have cosine and sine functions of the angles. And now one efficient way to describe it is to start in the first component with the sine of theta 1. And then we multiply this with sine of theta 2 and we continue until we reach the last angle. So this makes the first component quite simple. And now in the second component we do the same thing, but we use the cosine of theta 1. And otherwise the other angles are repeated with the sine function. Okay, and now after that, every component will have a cosine function and we will drop one angle after the other. This means here in the third component we have the cosine of theta 2 and then we will continue with the sine of theta 3 and so on. Okay, and now we just repeat this whole procedure here until the cosine function reaches the last angle theta n-1. Which also means that there are no sine functions on the left anymore. And that's it. This is how we can construct the whole vector just with polar coordinates. And maybe here it's helpful to quickly write down the standard three-dimensional case. Which means there we only have two angles, theta 1 and theta 2. So the first component has sine of theta 1 and sine of theta 2, and the second component cosine of theta 1 and sine of theta 2. And then we are already at the end because the last component is just the cosine of theta 2. And now this is one possibility for the spherical coordinates in R3. And now please compare this to the discussion in the last video, because you should see it's almost the same, just the interpretation of the theta 1 angle is different. More concretely, just the sine and cosine for theta 1 are flipped, but this does not change much. Okay, very well, and as promised, what we actually want to do here is to use the change of variables formula for an integral. Indeed, this is the key step. We have to make the substitution to change our coordinate system. This means let's first look at an integral there on the right hand side. So let's assume we have an integrable function f and we want to integrate it over Rn. And then, as already mentioned, we can just ignore a set of measure 0 in the domain of integration. Which means we can integrate over the image of phi without changing anything. And let's write the image in the short way, so we have the interval from 0 to infinity times u. And now comes the change of variables formula in. We integrate over this domain here and substitute x with phi. So quite simple, we have the integral of f of phi of r and theta. And please don't forget, our theta here consists of n-1 components. And moreover, the change of variables formula also tells us that the Jacobian determinant comes in here. So this is an important thing in the substitution, such an additional factor always comes in. And with that we have it. Now we change the variables to r and all the theta angles. So you could already say, this one here is integrating in polar coordinates, but of course we can make this whole formula much nicer. And in order to do that, we first should look at the Jacobian. This means we just have to calculate partial derivatives of this whole function phi from before. And in fact, the first one here with respect to r is quite simple, because we have this variable r in every component. And in fact, it's linear in each component, so it will just go out, and what remains here is a vector where no r is involved anymore. However, on the other hand, all the other columns still have this r in a linear sense. So without calculating much, we already know that we can pull out an r from each column. And obviously this fact we can nicely use when we want to calculate the determinant of this Jacobian. Namely, we can just pull out this r factor from n-1 columns. Which means in the formula here, our coordinate r only occurs as r to the power n-1. But then afterwards we still have to calculate a determinant of the remaining stuff, but we don't need to do that right now. Simply because we can build a nice connection of this determinant to a surface integral of the sphere. We immediately get that if we look at a suitable parameterization of the unit sphere in Rn. In fact, this is a straightforward generalization for what we have done in the last video. We just need to write down the parameterization. And as in the last video, let's call this one lowercase phi. And now it turns out, for the domain of the parameterization, we can just use our u from before. Hence, we can use the same theta angles as before, but we don't have the radius r as a parameter anymore. Otherwise, everything stays the same, which means with this formula here, we describe almost everything on the unit sphere. And this should not be a surprise, because if we take our capital phi and we set the radius to 1, we should get the unit sphere in Rn. In other words, this vector here is just our capital phi at 1 theta. But there's also a different interpretation, because we can also say it's the partial derivative of phi with respect to r. So what we have here is the first column of the Jacobian of phi. And most importantly, it holds for every r and theta. However, now the nicest thing for our surface integral here is that this is also a unit normal vector. Indeed, this is quite easy to see if we look at a two-dimensional picture. Now this vector here just describes the connection between the origin and the point on the sphere. And this means two things. First, if we shift this vector to the point on the sphere, we see it's orthogonal to the tangent vectors. And second, it also has length 1 because the vector describes a point on the unit sphere. Hence, we can use this nice unit normal vector in our Graafian determinant for the surface integral. And the common notation for that was the square root of g of the parameters. And it's defined by a determinant where we put in the normal vector and the tangent vectors. And there you know, the tangent vectors are given by the partial derivatives of the parameterization lowercase phi. And I say lowercase phi because this is the definition on the surface, but we already know we can actually replace it by our uppercase phi. This means in every column for the determinant here, we actually have our polar coordinates from before. More precisely, we have the partial derivatives of capital phi, which actually tells us that this one is related to the Jacobian determinant from before. The only thing missing here is the variable r, but there we already know it only comes in with the factor r to the power n minus 1. So by comparing both formulas, we immediately see that the Jacobian determinant and the Kramian determinant are connected in this sense. In other words, only the factor r to the power n minus 1 is the difference here. And obviously we can use that in our integration to get a nice formula for the polar coordinates. So again, in the first step, we can just use the standard change of variables formula to get in the Jacobian determinant. And then we can just replace it with the Kramian determinant times r to the power n minus 1. And moreover, of course, we can also use Fubini's theorem to split the integral up. This means we can write the integral with respect to r as an integral from 0 to infinity. And then we can also put the factor r to the power n minus 1 to the front. And then inside we also have the integral with respect to the angle, so we integrate over u. And now, as already explained, inside we have substituted the Jacobian by the Kramian determinant, which means we have this n-1 dimensional integral inside. And now the nice thing is that this one we can interpret as a surface integral. This simply means that we have a nice short way to write it. And actually for that we need the connection between our capital phi and our lowercase phi. But there you already know it's quite simple because it's just a factor r. Hence now we can finally use the definition of the surface integral. And obviously this will not change the one-dimensional integral over r. However, now we don't need the parameter phi anymore because we can just write that we integrate over the unit sphere in Rn. And what we integrate is a function f that is combined with a factor r. Which means the whole thing is easier to read if we use a variable, so let's call the variable on the sphere omega. So the area element d sigma here gets a variable omega as well. And that's it. This is the surface integral over the sphere, and it can be calculated by a parameterization like that. However, depending on the problem, this might not be needed, so this formula in the end can be really helpful. So this is the general formula for the polar coordinates, where angles don't occur anymore. So this is the general formula you can remember, and you see it's a volume integral that is split up into spheres. And maybe in order to close this topic, let's look at a quick example. There let's take a function f that is only defined in a ball in Rn. So more precisely, f of x should be given by the standard norm of x. However, only in the case that x lies in a fixed ball of Rn. Let's say it's BR0, so the open ball with radius r centered at the origin. And now outside of this ball, the function should be 0. This implies that our integration over Rn is actually just an integration over BR0. And now, as you already know, in this case we want to use our new formula for the integration with polar coordinates. This means the radius here is integrated from 0 to capital R, and inside we just integrate the function over the unit sphere. However, now the thing is quite simple, because it's just the standard norm of r times omega. Which means the factor r can be pulled out, and we just have to think what the norm of omega actually is. And this is not so hard, because we just integrate over the unit sphere, which means every vector on it has length 1. So we just have to integrate an additional factor r. So in total we just have to integrate r to the power n. And the remaining part is just a surface integral over the whole unit sphere. Which simply means this gives us the surface area of it, or in other words, the n-1 dimensional volume. Therefore the result here is just 1 over n plus 1 times capital R to the power n plus 1 times the volume of the n-1 dimensional sphere with radius 1. So for example, this volume is exactly 4 pi in the case that n is equal to 3. And with that we have it. Now you know a nice general formula for integrating with polar coordinates in n dimensions. And I would say in the next videos we can discuss some other integration rules which can be really helpful in calculations. So let's meet there again and have a nice day. Bye bye.